All right. It's time for inverse functions. I'm excited about it. I love inverses. You've seen them before. Big thing to remember here, swapping our x and y's, okay? And we're going to get into a bit more detail than that, but we're going to talk about, we're going to look at graphs, we're going to look at equations of functions, we're going to talk about verifying using compositions. I mean, it just doesn't really get a whole lot better than this, except for every day it gets better than this. Okay, it just always gets better. All right, so first thing, a function is one-to-one. I'm right here in this first yellow box. If any two different inputs in the domain correspond to two different outputs in the range. Okay, this is our more robust language for pre-calc counters. That is, if x1 and x2 are two different inputs of a function, f, then f is one-to-one if f of x sub 1 does not equal f of x sub 2. And that's generic to any 2 points, okay? So what that looks like graphically is if, say, we have, let's go with just our normal linear function, boom, like that. Or perhaps it could be something like that bad boy right there, right? A cubic function, not something where it gets, very dramatic, because then it wouldn't pass it. Let's see here. How about maybe a quadratic that's been restricted in its domain, so we only really see half of it. All of those would pass the horizontal line test, right? Any horizontal line only goes through it at 1 point, at most 1 point, only at 1 point there, okay? It could not hit the graph, like down here, it's not even going through it at all, down at the bottom below this graph, but again, at most only one time. Now, let's talk about ones that are not one-to-one, ones that would not pass that horizontal line test. So I'll do that in a different color here, just to switch it up. So if I had something like our square function or quadratic, right, that's not going to pass my horizontal line test. Maybe something in our trig functions like a sinusoidal function, right? That's not going to pass the horizontal line test. An absolute value function would be another one. I ran out of room, but right, none of those are going to pass the horizontal line test. It goes through more than one time. At most 1 point for the horizontal line test is all you got, okay? Now, this last box here I want to talk about, it's a little wordy. I'm going to get to the point. So if a function is one-to-one, we're going to describe what the inverse is. Jump down to here, okay? The correspondence from the range of f back to the domain of f is called the inverse function of f. Okay, so we're swapping those x and y's. We swap our domain and range. Everything flip-flops. If I switch my x and y's, my domain and range, which correspond to my x and y's, would also switch. Okay, we use the symbol f with that -1 there, f inverse, to denote the inverse function of f. All right, so let's get into some examples. All right, so for this one, we want to graph the inverse for the relation below. Put your answer on the same graph, and then find the inverse equation, right? We're going to often refer to these as a relation before saying that they are a function, because we got to see if it is a function. It does pass the vertical line test. And we also know the inverse is going to be a function as well, because it passes that horizontal line test. Always something good to check here. You'll see some domain restrictions in certain scenarios going forward. All right. So if we're going to graph this, I'm going to pick a couple ordered pairs here. I'm going to pick this one here, and then I'm going to pick, how about this one here, right, where I can see they clearly cross. Now, when I graph my inverse, I'll use a different color than red here. I'll use a sky blue. I'm going to switch my x and y's. So this ordered pair here is 0, 3. So 3, 0 would be an ordered pair on my inverse function. And this one here, which is 4, 1, it's going to be 1, 4. Right there. Lovely. Let me see if I can get a nice line. Boom, there we go. I just found the little ruler thing up here. That's pretty awesome. All right. I'll pop some arrows on there. So there is my graph of my inverse, right? And what we can see here, and I want to point out again that we talked about it, if I throw this at my on my y equals x, it's close enough. It would be 45 degrees. But, we won't do that. I could clearly see that it reflects over that line right there, right? It's always going to reflect over that y equals x line, that y equals x parent function. All right, lovely. So we've got our graph here. Now let's find our equation of this. So the first step here is to switch my x and y's. So I'm going to have x equals negative 1/2 y plus 3, right? And now I'm going to resolve for y. So I'll subtract 3. So I'll have x minus 3 equals negative 1/2 y, and then divide by negative 1/2, which is the same as multiplying by negative 2 on each side. And I'm going to switch this around. Y equals negative 2x plus 6. So f inverse of x is equal to negative 2x plus 6. I like it. That's it. That's all we're asking for there. We've got our graph, and we've got our inverse equation. First example done. Beautiful. As I already alluded to, we're going to have to restrict the domain. Look at the first part of these directions. Restrict the domain so the function is 1-to-1, and then sketch the inverse. We don't even have to write the equation on this one. Yay! So my domain here, if I want to make sure that it's 1-to-1, I got to make sure that it passes the horizontal line test. Where am I going to restrict it? Right here at my vertex. All right? So this value right here is where x is equal to 0. So I either have to be x is greater than or equal to 0 or less than or equal to 0. I'm going to go with x being greater than or equal to 0 for my domain. So we could write that as, if we're going with interval notation, from 0 to infinity. So I'm only talking about this portion of the graph. I'm not talking about the other portion. Well, I'll pick a couple ordered pairs to point out here. So here we go at 1, 0, and then it looks like you get a 2, 3, and we would know that just knowing the behavior of a quadratic function or square function. I'm going to switch colors here for my inverse. So for this first point of 0, negative 1, now it's negative 1, 0, which goes right here. For this next point of 1, 0, it's going to be 0, 1. And then for the last one, which is 2, 3, it's going to be 3, 2. I'm just switching my x and y's. Lovely. All right, if it helps to write them out, you can. Maybe I'll jot that down here just for this example. I did 0, negative 1, 1, 0, and then 2, 3. And then when I did the inverse, everything got switched. Negative 1, 0. 0, 1, and we can clearly see those 3, 2 on our graph. So we restricted the domain, and we graphed it. Awesome, fantastic, wonderful. When we restrict that domain, it passes the horizontal line test. It is a 1-to-1 function. We could not do the entire thing and call it a function, because if I had this portion of the quadratic function there, it now no longer passes my vertical line test when it's regraphed, so it's not a function. Okay, that's why we restrict the domain. Let me get that out of there. All right. Woo, we got a little bit more to this one here. Oh my goodness, the light's always going out in my room. There we go. You know, we're just saving the energy, saving the world, one light bulb at a time. Okay, so sketch the graph of f of x and its inverse. So we're going to sketch both of those. We're going to find the equation of the inverse and then also the domain and range. Quite a bit to do. I'm going to graph the original function first, and before I do that, I'm going to use, let's go with, I'll go with green on this one. I'm going to rearrange my function to look like this, and I think that's a little more visually pleasing for us to throw the x squared first, right? Put it in descending order. So when I graph this, I know that, let's see, we're talking about x is less than or equal to 0, so I'm only talking about over here on this side of the graph. So if I take my vertex, when I plug in 0, I would get positive 6. And then if I plug in 1, I would get, or sorry, negative 1, I'd get positive 5. And if I plug in negative 2, that would give me 4, but it's negative then, so that would give me positive 2. So I'd have these 3 ordered pairs. Again, I was just plugging in 0, negative 1, and I'll write them down. 0, 6, negative 1, 5, and then negative 2, 2. And we can see our usual, you know, we jumped 1 and then 3 in our y values like we do with our parent function of a quadratic, of a square function. Okay, so there's my wonderful f of x. Now for my inverse, when I graph that, I'm going to switch all my ordered pairs. I'm going to go with another color. Let's go with purple this time. So it would be 6, 0, 5, -1, and 2, -2. And when I plot those, it's right here, 5, -1, and then 2, -2. Yay, we had enough room. And I can see with my, I'm going to try and get 45. Come on. Yeah, all right. I can see with my ruler here, if I were to dash in a lovely little line here, I can see that those reflect over that diagonal line there, that y equals x line. So, boom, we've graphed it, right? Now we need to find the equation. So when I find the equation, and I will do that in purple because that's what the way I graphed it, I'm going to have x equals -y squared plus 6, and I'm going to resolve it for y. So I'm going to subtract 6 over. I'm going to change my sign, so I'm going to have -x plus 6 equals y squared, and then I'm going to square root everything. So I'm going to have y equals the square root of -x plus 6. Now, there's one last thing we need to figure out here, and it's that, well, when I square root both sides, I'm going to have a positive and a negative, right? It's plus or minus. But I can't have both in this situation. So which one is it? Well, we can look at our domain restriction to help us. If our x's were less than 0, our x's were negative, now our y's would be negative, our function is going to be negative. I'm going to toss that negative out in front. We could also see that this has been vertically reflected, which is outside the function, and it's been horizontally reflected, which is inside the function, because it's going upside down and to the left when normally it would go to the right and go up, right? So it's doing the opposite behavior. It has two reflections there. So that checks out with the graph here and the function itself. I'm happy with that. I like it. Boom. So when you're dealing with these, you're going to have that positive, negative, plus or minus. When you solve, you have to correctly choose which one, and we refer back to our domain for that, of the original function. Alrighty, so my domain of the original, and I will switch back to green for that. My domain for the original is from -infinity, right, because it's going to the left and continuing, and it ends at 0. So -infinity to 0, bracket. And my range is all the way at -infinity. It's going down, right? And where does it stop going up? Stops at 6. So by looking at the graph and also knowing behavior of these inverses, we should know that these are just switched. Let's see if it is. My domain is going from -infinity, and it stops at +6. Look at that. The exact same as the range from the function. And then the same holds true here. I'm going to be going from -infinity to 0 for my my range, which is my domain from the original function. We did it all. That was a lengthy problem, but we did it all. That was awesome. Fantastic. America, freedom, rock and roll. All right, so same kind of question here, but we're, with all the domain, range, find the inverse graph and all that. But now we have our square root function here instead of dealing with the square function, the quadratic, right? Okay, so I'm going to do my original function. Let's do red for my original function. And for this one, let's see here. It's normally would start at 0, 0, but we have a shift left, so I'm gonna shift it here. And then I know, so we have the ordered pair of -1, 0. And then my next one, if I plugged in 0, I'd get 1. And then I'm going to pick another, so I get an integer. If I plugged in 3 for x, I'd get 4 inside. Square root that, I get 2. So 3, 2. And you could also just know the up 1 over 1, up 1 over 3 behavior of a radical, right? Or of a square root function. So I've got my graph of the original. Now let's get the inverse, and I'm going to go with, how about blue? So I'll just switch my ordered pairs. You could write the equation right now and then graph it from the equation. Since I have some ordered pairs, I find it very easy to just do this. So 0, -1, 1, 0, and then 2, 3. And again, I don't mean to overstate it, but I will. We can again see these are reflecting over that line, you know? So that's pretty wonderful to see that each time. It's good to verify that so you didn't do the wrong portion of a graph or something like that and it looks weird. So now I'm going to go ahead and find my inverse. So x equals the square root of y plus 1. And I'm going to pause it here and just have the work run out so it saves a little time. So let's pick it up here. I have the inverse is x squared minus 1. However, that is a parabola, a quadratic function, a square function that would make a U shape. I have to restrict my domain. So there is a little bit more to this, and we'll put where x is what? Well, I want the positive side, so greater than or equal to 0. That's where this graph is starting. So seeing that graph also helps with that domain there, right? So this would be my answer for right here. All right. Oh, that's an H. My apologies. There we go. So for my domain of the red one, the original function, the h of x, I am starting at, oops, let me change colors here. I'm starting at -1 and I'm going to infinity. My range is starting at 0 and going to infinity, right? Because I'm going to the right and up. Cool. And then for the domain of my inverse, we know that those are going to flip-flop, but let's verify it. It starts at 0 for my x values and continues to the right. And then my range, it starts at -1 for my y values and continues going up. Bibbidi-bop, done. Awesome. Main thing here, guys, that domain restriction when you write the function of the inverse, okay? The inverse function. So skipped over a couple problems in the guided notes. We're gonna hit this one from the second page though. Verify that the two given functions are inverses by showing that g of h of x equals x and h of g of x equals x. Give any values of x that need to be excluded from the domain. When we're looking at these two functions, they're both linear functions, they're lines. We don't have to restrict anything from the domain. Those are when we have radical functions, rational functions. Those are things where we have to look out for, right? Okay, so first I'm gonna do is g of h of x. And if I do that, that means h of x is being plugged into g. So I will have 6 and then 1 over 6 x plus 2 substituted in for x minus 12. And I'm just going to go through the algebra here, distributing. So I'm going to have 6 times a sixth is just going to be 1x plus 12 minus 12. That equals x. Boom. I like it. Red check mark. The next one I'll do in green. We're going to have h of g of x. So g of x is going to get plugged in to the x here. So I'm going to have 1/6 and then 6x minus 12 plus 2. Distribute, I'll get, again, x because it's 1/6 times 6 minus, and then 12 times 1/6 is 2 plus 2. That equals x. I'm going to go with that red check mark again. Whoop, whoop. They both equal x. We've verified that they are inverses of each other. We did not need to restrict the domain in any way. We are done with this problem. I'm moving on. All right, using some compositions here. And I feel like these can be kind of confusing. I was really going to think about them a little bit. I know when I first approached these problems, they can be a little bit troublesome. So here we have f of 2 is equal to 3. And we have g of 0 is equal to -1. We want to find these here, okay? So f inverse of 3, what is that going to equal? Well, if f of 2 is 3, that means the ordered pair 2, 3 is in the original function, which means my inverse function is going to be 3, 2. So this is my f, and then this is my inverse of f. Well, what's the inverse of, if I plug in 3 there, f inverse of 3 is going to give me 2. Okay? So we're just, it's flip-flopping the x and y's, really, is what's happening there. So you might be able to gather the same kind of thought process here in this one. G inverse of -1. Well, I know that if g of 0 is equal to -1, I'm going to flip-flop my x and y's, bibbity-bop, boom, that one's going to be 0 there. because now my y value is my input, my x value from the original is my output, okay? All righty, next one, f inverse of f of 2. Well, if f of 2, that's going to be 3, right? What's f inverse of 3? That's just 2. Dunzo. All right, so another thing we could jot down here is if a comma b is on f of x, then f of a equals b, so f inverse of b equals a. Okay, we're doing that little flip-flop. X and Y switch in inverses. Cannot stress that enough. Alrighty, let's continue. Now we're going to interpret the inverse of a tabular function. That's a fun word, tabular. I like it. I'm gonna use that more frequently if I can. So it says f of t, a function of time, is given showing the distance in miles that a car has traveled in t minutes. Find and interpret f inverse of 70. Well, remember with inverses, we're just switching our x and y's, right? Our input and output switch. So f inverse of 70 is going to equal 90. Boom, first part done. Interpret it. Well, we could say that when does f of x equal 70, or maybe after 70 miles, after 70 miles have been traveled. "90 minutes have elapsed." Cool. I like it. Except for the fact that I put maybe one too many L's there for elapsed. I'm going to fix that. There we go. Boom. Awesome. All right. So some of these problems will ask you to like interpret what the heck's going on. Usually we think about like, oh, as this amount of time has passed, I've traveled this much. But then we're thinking about it in reverse there with the inverse. After how many miles that I've covered 70 miles, how many minutes have elapsed there? We're just going to flip-flop it. Cool. Moving on. So now we're going to evaluate a function and its inverse from a graph at specific points. Okay, so we have g of f graphed here. This is an exponential growth function, if you remember your parent functions, which we've reviewed. Let's see here, g of 3. Find g of 3. Well, g of 3 is just going to be right here, which is 1. So g of 3 is equal to 1. Boom, done. And g inverse of 3, well, this is not just 1 or anything like that. We got to think, okay, my output value from my original function was 3, and now I'm evaluating that, right? So when, so to speak, when is g of x equal to 3? That's the question we could be asking here. Well, when on this graph is my output 3? Well, that would be right, and I'm going to change colors here real quick. That would be right here, okay? So when x is 5, that's when I get 3, which means that g inverse of 3 is going to equal 5, okay? A little bit of a thinker there when you start looking at these graphs. I like it, though. I like thinking. I like making that mind work. And that was actually it. I thought we had one more, but, you know, I was fooled. I'm just always looking for more math, you know? I'm always looking for more math. Hopefully you guys enjoyed some inverses here. A bit of it was review. Maybe some more was like, holy cow, I totally forgot about that. Right? I didn't know that. That's exciting stuff. Always good to learn something new. Hope you guys have a great day. And, you know, America Freedom, rock and roll, Costco. Follow Riverdog Jenny if you haven't done so already in the gram. She's the best. You guys are the best. Peace.